of an intermolecular force. What does that even mean? Abbreviated IMF. If we look at a molecule like water, what do we call the bond? What kind of bond happens inside that molecule between the oxygen and the hydrogen? What type of bond is that? Polar covalent. And based on the shape, this molecule, we said, those polar covalent bonds don't cancel out, making the entire molecule polar. And the more electronegative atom, the oxygen side, becomes somewhat more negative, and the hydrogen end becomes somewhat more positive because of the way the electrons are unequally shared across the molecule. But this is not an intermolecular force. This is an intramolecular force. So a covalent bond, an ionic bond, is internal. So this is inside the molecule, if I can put it that way. Now, for what we're going to explain in this unit, there has to be at least two molecules present, because we're looking at the interaction between one molecule and another, or many. But when I say intermolecular force, I mean between separate molecules. And that's really the first main thing you have to understand. So I can't even define an intermolecular force until there's at least two molecules. They don't have to be different, just two molecules. So can you imagine that if I took, let's say, something like HCl, which based on its Lewis structure is polar, because again, chlorine has a higher electronegativity than hydrogen. And the polarity, or the dipole moment, would be directed this way. It's obviously a simple linear molecule because there's only two atoms. But when you look at this, the negative side will be by the chlorine, the positive by the hydrogen. But can you imagine that if there was a second molecule nearby, let's just put it over here. Can you imagine that these two molecules, being dipoles, could attract each other? Would they attract each other? Where and why? Well, we don't have to be that specific.
Negative and positive.
Yeah, don't they have oppositely charged ends like little magnets? And so we can imagine, and I'm going to use dotted lines to show these to indicate that these are different kind of bonds. But this dotted line here is an IMF. It's an intermolecular force because it's an attraction between different molecules. That's the whole subject of this chapter. So understanding what that means first, and then second, what types of intermolecular forces are they? How do their strengths compare? And how does knowing this tell us anything about the properties of the substances in which these intermolecular forces, or between which these intermolecular forces occur? That is the moral of the story. And that's what we're going to build on today. So the one I just illustrated is the easiest one to visualize. It's called, quite literally, a dipole-dipole force, because it's the attraction between two dipoles. And I start with this one because, like I said, it's to me the easiest one to visualize. For abbreviation purposes, I like to call these dip-dips. Dip, 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 for those of you who like 50s music. Anyway, the dipole-dipole force has the following requirement. It occurs between polar molecules. Notice the between, meaning there has to be at least two. So in order for us to be able to establish that a dipole-dipole attraction happens, we must first be able to establish the presence of polar molecules. And that's what we learned in the last unit, right? We learned about the fact that certain molecules are polar by their structure. So Let me put this up, it's a little bit more formally nice with pictures. So, dipole-dipole attraction between polar molecules because the opposite charged ends of the molecules attract. And here's an important aspect of it. The strength of this force will increase as the dipole moments of the molecules get stronger. Meaning that if we have more and more polarity, the degree of charge separation is stronger. It's like having two stronger magnets. So the more the difference, or I should say, the bigger the polarity of the molecule, the stronger this dipole-dipole attraction will be. And it's really just that simple. Let me show you a little simulation of it. So it might look something like this. Here's a bunch of little polar molecules. Notice they're lining up in ways that are favorably attractive. Opposite ends attract, and so they align that way. And that attraction holds them together. This is why, or how, we might start to think about the following. Why do dipole substances form liquids? In other words, something like water exists in this room as a liquid. Why? Why do the molecules come together and stick to each other like this? It has to do with attractions between the molecules and the strengths of those attractions. What's stopping it from being a liquid? What's trying to force it to be a gas? What factor is going to turn a liquid into a gas, primarily? Heat. Yeah, heat or temperature. And so we're going to see this interplay of these properties between how strong are the attractions holding it together versus how violent are the motions trying to throw it apart. And that interplay is going to be a lot of what we talk about with these properties that I'm going to define as we go. Any questions about recognizing a molecule that can do dipole-dipole attraction? What do I have to look for? If the molecule is polar, correct. So that's step one. Now water has a very special type of dipole attraction. In fact, it goes beyond just being a simple dipole attraction, and so it gets its own name. But this is probably the most important of the intermolecular forces, because of especially its role in biology. But the hydrogen bond is a very specific effect, and it's considerably stronger than a typical dipole-dipole attraction. Notice very specifically, I've defined three elements that undergo or can cause this type of intermolecular force. These three elements in particular. What's special about them? These three elements are the most electronegative. Why those, and why is hydrogen the other piece of this? Please be careful. Again, let me draw the water molecule, even though I have it. This bond is a covalent bond. This is not a hydrogen bond. A hydrogen bond exists between molecules. There has to be at least another water molecule to explain this. Here are the two key factors you need to make a hydrogen bond. You need either N, O, or F directly bonded to a hydrogen atom somewhere in the molecule. Notice water has that. It has oxygen directly bonded to hydrogen. The other thing you need is a lone pair, because it's that lone pair of electrons that the hydrogen on molecule 1 is going to attract to. Let me explain why this is such a special case. When you think about a hydrogen atom, isn't it just a proton, which is very tiny positive charge? Like in terms of physical size, a proton's very small. And it's got one electron around it, which we can show with this 1s electron cloud. But what happens when a super electronegative atom is pulling on the electrons? It pulls them more toward itself. And so what you effectively get is almost, not quite, when the electron density gets shifted toward another atom, you get almost a naked proton, just kind of sticking out of the molecule. Well, that charge is very exposed and very small, and it can get very close to the lone pair on the next molecule and make a pretty strong attraction. That's why this special case. So notice this dotted line. In this case, this is a hydrogen bond. Again, it's the attraction between the two molecules, not within a single molecule. This is extremely important to see the difference. But among all the intermolecular forces, these are probably the strongest pound for pound. So, the dipole-dipole force, you just need polar molecules. The hydrogen bonding is this special case where you need this particular linkage and a lone pair. And it becomes far stronger in terms of that attraction. It's why water is a liquid on Earth at these temperatures. Any questions so far about these first two? Because they're pretty straightforward. Like, am I making any sense to you, or is it completely like, phew? I mean, obviously we haven't applied it yet. I'm just trying to generate the idea. Okay. So these are not hard because we have established permanent dipoles that interact. The hardest thing to explain and understand is, what about nonpolar molecules? How is it possible that nonpolar molecules stick to each other? It doesn't seem like there's any charge anywhere. It's all balanced out, it's all equally distributed. What is going on with the nonpolar molecules? Well, that's the hardest one to understand, but luckily for you, I've got some really nice little simulation stuff to help you visualize it. What do I need again if I want to do hydrogen bonding? I'm going to put it up.
Nitrogen, oxygen, or fluorine.
Specifically?
Bonded to a hydrogen.
So I need either an NH, an OH, or an FH somewhere in the molecule. And what's the other thing I need?
Lone pair.
I need a lone pair. Okay, good. Now the last one, bless you. Well, this one is called London dispersion force. London for a person, not for the place. And I'm probably just going to call it dispersion from now on. You can call it London force, you can call it London dispersion force, you can call it dispersion force. But this is the one that happens, I should say occurs, between all molecules. So every kind of molecule will have this happening. However, and this is the important however, it is the only intermolecular force between nonpolar molecules. In other words, without this, the nonpolar molecules, we wouldn't have a way to imagine they stick to each other, to attract one another. Okay? Now I'm gonna kind of slide into this with a little bit of physics first and see what you guys think. So I have here a dead rabbit. Well, it's skin.
Nice.
Real?
I figured, you know, I come from a school of thought that you should never waste anything. So one time I was driving home from work and I hit a rabbit with my car.
No, you didn't.
There was just squealing noise, and I saw it fly through the air, and I'm like, well, I might as well just take it now. Luckily, I had my butcher knife and my tanning supplies. Always carry them just in case. I ripped the thing's guts out, tore off the hide, and then I set it up. So this is it. Actually, we bought this from the store. Anyway. Also doubles as a one of those in case I'm going out on a hot date with my wife. Rock concert. Wee-wee? All right, so here's what I want to show you with this. Luckily for us, this school is dry as a bone all the time, so static electricity is easy to generate. So I've got this PVC pipe so I can make a little static charge on it. And the thing is, when you have an insulator like plastic, when you put an excess charge, it stays there. It doesn't spread very easily. Insulators don't allow electricity to flow through them very well. Now watch what I'm going to do here. This piece of styrofoam is also basically an insulator. Okay, so if I rub this, you can almost hear the clicking. You can probably hear the clicking. And I put it nearby, it doesn't really do much, which makes sense. That's neutral, right? I charge this up. Ow. Got a shot. But it couldn't attract the neutral thing, right? All right. Now watch what happens when I do this tin foil covered balloon. And I don't know if you guys ever learned this in physics, so I'm teaching you physics now. Ready? Remember, this is neutral too. Seems like it's being influenced. Seems like I'm attracting it. Oh, did you see that? What the heck? Wait a second. How can something neutral be attracted by something charged? That's really kind of the important question. So this is charged now. I charged it up. I put this nearby, and it literally pulls it. Didn't do it for this one.
That's how magnets work.
Not exactly. They have a force that seems to transmit through empty space. That's true. But this phenomenon is quite different. What I'm showing you here is a process called induction. It's why you can rub a balloon on your head. I can't. And stick it to a wall. Right? So let me kind of give you a loose explanation of what's going on here and how it connects to these dispersion forces. So if I take, and imagine that metal-covered balloon, okay? The thing about a metal is that electrical charges can move around pretty easily on the surface. And so I have a bunch of positive charge, and I'm just going to show this oversimplified, okay? And negative charges that when they're equally distributed, when it's not polarized, they're all on top of each other. And it's neutral, and it's not polarized. But if I take that rod and I charge it with a negative charge, then for simplicity, I'm just going to show the excess negative charge on here. What's it going to do to the electrons that are free to move? Which way is it going to push them?
The other way.
They're going to get pushed back, right? Now the positive charge can't really move very well. It's kind of locked up in the nuclei, right? It's the protons. But look at what happened. This is still neutral, but now it's kind of polarized, isn't it? But why is it polarized? Because something else charged nearby made it do that. And look at what happens. Now that it's polarized, doesn't this negative charge feel closer to these positives and farther from these negatives? And doesn't Coulomb's law tell us that the strength, at least in part, depends on how far we are from the charges? So overall, there's a net attraction. That's called induction. We're inducing polarity by using something charged. Does that make sense, that I was able to attract something neutral this way? Yeah.
So you're basically pushing the electrons away, which like makes a fake polar kind of thing?
Yeah, like a temporarily induced dipole. I've literally temporarily induced a dipole. Temporary because when I take the rod away, the charges just go back to their original distribution. But in the moment that it's like that, it works. It attracts it. Now, is there some way to explain this when we look at a nonpolar molecule? Because there's not little dead animals and rods going around in between molecules, is there? Or is there? Well, let me show you what this might look like. If we could zoom into the molecular world. So first, let's look at an electron cloud around an atom. Remember, an electron cloud is not like a hard shell. It's the movement of an electron within a region of space around the nucleus. So you see the little mambo it's doing? This is just random fluctuation. It's just random. Once in a while, the electrons might be on this side or that side for a moment. But while it's fluctuating, look at what happens. At any given moment, there's a little temporary dipole that's just random fluctuation. So even though it's a nonpolar molecule, the fact that the electron cloud is just kind of jiggling at any given moment makes it lean one way or the other. Can you swallow that idea just conceptually? It's just randomly jiggling. Like if I had a water balloon and I slapped it and it was going, or a bowl of Jello, or
Because
me.
they have energy?
Huh?
Is it because they have energy?
Yeah, it's because they're moving, right? The electrons are not just static. They're constantly moving around the nucleus, although we can't really pin them down. At any moment, we can at least imagine that they're not equally distributed just by random chance. Now, watch what happens if another molecule is nearby. Now we're getting the induction effect. In other words, if this one randomly fluctuates, it's going to influence its neighbors just like my charged rod did to that foil-covered balloon. In the moment that this is polarized, it can polarize its neighbors. And in that moment, it attracts. Now this is fluctuating, so it's not turned on all the time. But if this is happening zillions of times a second, on average, it's like having one continuous force. It's kind of like having a strobe light. It's turning on and off, but if it flashes fast enough, it just feels like the ring is kind of lit up, even though it's turning on and off all the time. What's that?
Like these lights.
Yeah, these kind of do that too. They fluctuate. Now, what's going to determine how easy it is to do this and how effective it is, like how strong it's going to be? Well, certainly the more electrons I have to fluctuate, the more fluctuations I can make, and the more easier they are to move around, the bigger the fluctuations I can make. So let's see what that looks like. So check out like a big long molecule. Again, this is exaggerated, but it's just trying to show you that the electrons of the valence shell can be moving around in lots of different spots. And all those little spots where it's moving around are places where it can temporarily be polarized and attract other molecules. So this is the idea of dispersion. I know it's kind of hard to swallow, but it's really the only way we have to understand how nonpolar molecules can stick to each other. And if you're wondering, is this really strong? Well, in small molecules, it's very small. That's why helium, which is just a monatomic gas, we know there has to be some attraction because it liquefies. We know it's weak though, because it liquefies at 4 Kelvin. Literally like 4 above absolute zero. You have to get it that cold before helium atoms' attractions are strong enough to hold them together. But why? Because the helium atom is one of the smallest atoms there is. It's a really tight electron cloud, and its fluctuations are going to be almost non-existent. But then you take something like oil. You guys ever cook with oil? Oil's nonpolar. It's long hydrocarbon chains. We said hydrocarbons are generally nonpolar. But oil has a higher boiling point than water. Water has hydrogen bonds, which are the strongest type. But oil molecules are so long and big that this van der Waals, kind of London dispersion, I should say, can actually grow pretty sizable overall. So that's part of the argument we have to think about. It's not just pound for pound, but how much total bonding is happening that influences how strong the bonds are. So let's look at this kind of in summary and see if I was able to make this any sense, because there's some specific language you have to use when you're explaining this on paper. Okay, so we've already said the dispersion forces happen between all molecules, but they're the only type that we have for nonpolar ones, and that's why they're so important to the nonpolar ones. We've described them as temporarily induced dipoles that are based on these fluctuating electron clouds, inducing temporary polarity in their neighbors and causing attraction. Here's the important thing here. This bullet point is the most important one on this screen. The dispersion force will increase with an increasing number of electrons. Now we can loosely tie this to the molar mass, but it's not because of the mass. It's just coincidental that as the molecule is larger, there's more and more layers of electrons around it. Here's the key term. This word, which I bold-faced here and capitalized, you need to use this term. Polarizability. The ability to make the electron clouds shift around. Anytime you're going to argue that something has a stronger dispersion force, you must use the language, it's more polarizable. What makes it more polarizable? More electrons. That's the key point. Now there's other subtle pieces to that. For example, surface area. Surface area is another key factor, because the more points of contact you have, the more places these fluctuations can lead to attraction. Think about the difference between gluing 2 bowling balls together, which are spheres that they can just touch at one point, and gluing 2 sheets of paper together, which are very spread out, and you can get lots of contact space. You can get a much better attraction or sticking of 2 sheets of paper than you can 2 bowling balls.
So does that mean that planar molecules will stick better?
Very good. In terms of dispersion, long, flat chains molecules are going to have a lot more points of contact. And we can show that in the data. We can show how this influences the properties. So, let me put, for our last, on our list here, the London dispersion forces, which we can just say dispersion from now on. So we said this occurs in all molecules, but it's the only thing that we have to explain for the nonpolars. And and that's where they're probably most important. It depends primarily on, I'll write it this way, strength depends on number of electrons, which is going to, again, loosely associate with molar mass because bigger molecules have more electrons. Surface area, meaning points of contact, but together, put these together and talk in terms of polarizability, the ability to deform the electron cloud. Another good way to think of polarizability, if you ever tried to sleep on a couch and you know the pillow's really stiff, it doesn't move much and so it's not comfortable because you can't really deform the pillow into a nice shape. But if you have a nice big cushy pillow filled with, you know, like dead animal feathers, dead bird feathers, it's really mushy and you can really deform it, that's much more polarizable. It's cushy, it's mushy, and you can reshape it into different ways to make it more comfortable. Same idea.
It's a serious matter.
All right, it's all right. Dead animals are here for a reason. Okay, so let's look at some applications of these and see if we can start drawing some conclusions. I think it's important to note that if we go down, or I'll go up the list, and we have to be careful when we say this. This is only when we're comparing similar sized molecules. Because as we showed, this one largely depends on how big the molecules get. But when comparing similar sized molecules, as we go up this list, the London dispersion forces are the weakest for similar sized molecules, and the hydrogen bonding are the strongest. But all of them are considerably weaker than covalent and ionic bonds. This, at most, might reach 5 to 10% the strength of a covalent bond. That's not insignificant. But this is why I know when I boil water, I'm breaking the intermolecular force, not the covalent bond. If that weren't true, then when you boil the water, you make a mixture of hydrogen and oxygen gas, and then it would explode over your oven. This has actually happened, but not there. There are some chemical fires that get so hot, if you spray water on them, it decomposes the water and causes a secondary explosion. You have to use special chemicals to put those kinds of fires out. Now, your stovetop's not going to do that. That would be not good. I'm making tea. Boom, there goes that. Let's try to explain some data now, and then we're going to kind of segue into properties and go into kind of the lab demonstration phase of our program. Take a look at these data. For now, I think it's fair to use melting and boiling point as a surrogate for how strong the attractions are. Because again, when molecular substances are boiled or melted, it's the intermolecular forces we're typically interrupting. So take a look at the noble gases, where it's just really these very weak dispersion forces between the atoms. Here's their molar masses. Notice the boiling points. Why are the boiling points getting higher, meaning more positive, as we go down this list? What must be the reason? Not electronegativity, because these are all monatomic. It's not to do with polarity per se.
They're bigger.
And as they get bigger, what do they have more of?
Electrons.
And if there's more electrons, the electron cloud is more, what's the word?
Polarized.
Polarizable. So as you're going down this list, more and more electrons means more and more polarizable cloud means stronger dispersion. That's the argument that you must make. Now look at these ones. These are all nonpolar molecules too, right? But look at the range. What the heck is happening here? This starts at negative 188, which is comparable to maybe argon. Interesting that their molar mass is about the same too, isn't it? So their electrons are going to be about the same. But why, by the time we get to iodine, this is higher like than the boiling point of water. That's why iodine in this room is a solid. What the heck is going on here? Well, it is a lot heavier, so there's more electrons and it's more polarizable. But remember, this is monatomic. So here's one helium, here's another, one point of contact. Iodine is a molecule, so it's more like a sausage shape. When you have two sausages next to each other, aren't there more points where dispersion can happen? So even though both of these are based on just dispersion and nothing else, the increasing number of electrons, the bigger surface area combine to make a much stronger overall intermolecular attraction. Yes?
Oh, so in that diagram you just showed with the sausages, there's 4 I's, but there's only I2.
Well, these are two separate molecules.
Oh,
This is
so
an
one
I2.
molecule of iodine, okay.
Yeah, otherwise we can't even discuss intermolecular. We have to have at least 2 molecules, right? And then here, again, you just have to remember hydrocarbons, pure hydrocarbons are nonpolar. That's very useful to know. But you see it's the same effect. As we're going down the list, as there's more and more carbons and hydrogens, there's more and more electrons, you can see again the boiling point increasing because of the greater number of electrons and the greater polarizability. Any questions? Yes?
Can I go back?
Yes.
So more electrons, more polarity.
More polarizable. Because remember, nonpolar molecules don't have any built-in polarity. It's the fact that they can be distorted and temporarily induced into being polar. That's the key point. Right? The other types, there's some kind of polarity or kind of permanent opposite charge to interact with. That's what makes those easier to visualize. This one's hard because you have to imagine these fluctuations. Now, this is just more of the same. I think this is an important stepping off point to start comparing what happens when there's more than one intermolecular force at play. So what I did here was I picked simple molecules that had similar masses so that their electron counts would be similar. Nitrogen and carbon monoxide are very similar. Why is carbon monoxide's boiling point a little higher? Why is the attraction between CO molecules slightly stronger than between N2 molecules?
It has some dipole force.
Good. Because this is a polar molecule, this is not just dispersion anymore. This has dispersion and probably very similar dispersion to the nitrogen. But because carbon monoxide is polar, this also has a dip-dip attraction. And that adds more attraction because, again, we can have more than one intermolecular force operating at the same time. Just like you can glue and tape something if you want, and staple it. Different ways to bind it, but more binding. And you can see this pattern down the list. Each time I try to compare things that had similar dispersion, and each time it's the polarity and the dipole-dipole attraction that explains why this side is continuously harder to boil than this side. Does that make sense? Can you see what I'm saying? Because later, you're going to have to be able to take groups of molecules and compare the relative strengths and like, okay, why does this one have a higher boiling? Why is this one more viscous? Why does this one have more surface tension? All of those are going to be meaningful in just a minute. Perhaps the most important graph is this one. This graph beautifully shows everything. I can explain everything we just learned in one graph. Okay. So first let's interpret what this graph is showing. It's a plot of boiling point versus molar mass. Again, molar mass is really a sit-in for number of electrons and strength of dispersion. So if you look at CH4, SiH4, GDH4, SNH4, all of these are related because carbon, silicon, germanium, and tin are all in the same family. So these are all very similar molecules chemically. But because of the increasing molar mass, what force is there more of? Since these are all nonpolar tetrahedrons,
More dispersion.
yes, we see dispersion increasing, and that explains the first purple line. Because there's more electrons, there's more polarizability, we get more dispersion. And that's why we see this trend upwards in boiling. Now watch this. H2S is very similar in mass to SiH4, but it's higher in boiling. And these patterns also show that same thing. They're all in the same family as well. Why is it, if they have similar dispersion to the ones directly below them, that these are all higher in boiling point? What do they have that's different? What kind of molecules are they? Say it. They're polar. Because these are all polar, these have dispersion, but they also have dip-dip. That makes the total intermolecular force between these stronger than these. But do you see how they still follow a pattern of increasing with more molar mass? That's due to the excess, or the increase in dispersion. But then you have this whack job way out here, water. Water is the smallest of that group, but it's by far the highest boiling. What must be happening there? Good. So does this have some dispersion? Sure. Big deal. It would have the least dispersion of this group. Does it have some dipole-dipole? Probably. But the real key to the water is the hydrogen bonding. This blows everybody away. It's the OH groups that allows the hydrogen bonding that really puts this anomalously way out here. And so you can see all the things I just talked about overlaid right on this one thing. Beautifully. Now to kind of conclude this summary of intermolecular forces, let me show you an entire spectrum and see if this makes sense. Some of them I didn't talk about directly, but they all kind of follow from the same pattern. So the ones that we did talk about directly: hydrogen bonding, dipole-dipole, and dispersion. What are these other goofballs? This one's important when we talk about, if you remember back in Unit 2, we did ionic compounds in solution, and we talked about how water molecules surround ions. Well, there's a pretty strong attraction between a dipole and an ion, because ions are fully charged, and dipoles have charged ends. So we call this an ion-dipole force. It's even stronger than the hydrogen bond. Then we have our hydrogen bond, our OH group on one side, attracting a lone pair here. Then we have our permanent dipoles attracting opposite ends. Here we have an ion, just like my rod here, inducing charge in a nonpolar molecule. So this is called ion-induced dipole. You don't have to know it, really. I'm just trying to show you it's just the full spectrum. It just shows all the possibilities. Here you have a dipole-inducing dipole, and here you have dispersion, which is, again, the random fluctuation. But I thought this was a nice graphic, because it really showed the full spectrum.
How do you know if the bond is dipole-dipole?
As long as both molecules interacting are polar, they can form a dipole-dipole attraction. Can there also be dispersion? Yes. Can there also be hydrogen bonding? Yes. So some of them are going to have multiple layers of intermolecular force.
But dispersion occurs in all of them?
Yes.
Okay.
Any other questions before we move on? Yeah.
And we're looking for the highest level of bonding, basically, when we're...
Ultimately, right now, all we really saw is how to determine what kind of bonds are possible. When we're going to compare strength is when we're now going to start looking at how does it influence the properties. Why is this thing different than that one, like we just did with boiling point, right? But there's more interesting properties to consider, and we're going to start looking at them. My goal is if you understand this, you'll be able to apply it right away and be like, oh, that's why this one is more than that. That's why this pours more smoothly than this. This is why this evaporates more easily. Stuff like that. Once you know what the terms are, you'll be able to apply this and explain it. That's the goal. Let's see how it goes. So, oh, he's already answered. Oops. Move on. All right, so what I'm going to now do, by the way, that was perfect timing, is I'm going to go through these types of properties, and I'm going to demonstrate things, and as I do, I'm going to explain what they all mean. The liquid molecules, some of them are going fast. Remember, there's a distribution of speeds. Some go really fast, some go really slow, most go to average speed. But near the surface, if a molecule is going fast enough, it escapes. And that's what evaporation is. So what's going to control the rate of evaporation? Two factors. What's going to affect how fast something evaporates?
Strength of bond.
Temperature. Good. You got it right on the money. Rate of evaporation is going to be based on two things. Temperature is one of them. One of them is the strength of the intermolecular forces, because the stronger they're attracted to each other, the harder it is for them to break free. And the other one is the temperature, because the temperature determines how much energy they have running around in the body of the liquid. So let's make sure we understand the relationship. When the strength, I'll make a little table up. And can I give you a measurable way to describe the rate of evaporation? Because if you do it in a closed container, you end up getting a constant pressure. So we can call it vapor pressure. So that means that, and I'm going to demonstrate this in a minute, but the vapor pressure, if the strength of the IMFs are high, what should that do to the tendency to evaporate? Make it high or low?
Low.
So when it's a strong attraction, the tendency to evaporate should be low. Does that make sense? Because they're more stuck to each other? They can't get away as easy? What about the temperature? If I raise the temperature so the molecules are moving faster, what should that do to the tendency to evaporate? If they have more energy, doesn't that make it easier for them to break free? So I'm going to do an experiment here, a real simple and stupid one actually.
Nice.
Thank you. Where I'm just going to take two liquids and put them in these flasks, and I'm going to control for the temperature because they're both going to be at room temperature. Then I'm going to shake them up and try to get them to evaporate and establish a pressure inside. And then you have to listen really closely because I'm just going to make them burp.
You do the craziest lab you've ever done.
What?
You do the craziest lab.
The craziest lab I've ever done. Now what's interesting about vapor pressure is it doesn't matter how much liquid I put inside, as long as there's some liquid and some vapor, we get an established equilibrium. So hello.
Ask up. You know where Clem is?
No, you're the second person looking for him. Will you owe people money or
Ask
something?
up.
Okay, so I want you guys to imagine that as soon as I sealed this, water molecules were evaporating, and within a fraction of a second, they established a constant pressure in here. Because what's going to happen is the ones that evaporate go into the space above here, and they're bouncing around, and since I trapped them, they start falling back in. And so I get a constant vapor pressure right there. Okay, now, I'm going to do, that's water. I'm going to take my acetone, which is a whole other liquid, and do a similar thing.
Big red warning.
About equal amounts of both, and I'm getting them both in there. Now, before I actually do the experiment,
I said equal amounts?
about acetone's more expensive, shut up. Okay, now, here is the molecular structure of water, and I'll draw it out for you, although that one you should know. Acetone looks something like this. Now, before we get too far down the road, let's make a prediction. What types of intermolecular forces should exist between water molecules? Certainly hydrogen bonding is the most important, but wouldn't it also have the ability to do dipoles and dispersion, because everybody has that? But what about in this one?
I say H bonding.
I don't see how you could get H bonding in this, because
There's no H and O.
there's no direct link.
I say dispersion.
But I would definitely agree with dipole
Dispersion.
and dispersion,
Wait, why is it dipole?
because this part, even though I drew it flat, is bent, and the oxygen adds polarity to the structure, because it's very electronegative. Okay? Now, let's do this. Let's energize these suckers up a little bit. Really get them to evaporate as much as they can. I can only do this once, because once I do this, that's it. I can't make it happen twice. Ready?
Oh gosh. Okay.
I'll do the water one first. Listen for it to, like a little burp.
Oh, I heard it.
There was like almost nothing.
I didn't hear it.
Yeah, okay, now listen to this one. That's why I'm saying this is a really lame demonstration that's probably going to fail. Now listen carefully. Did you hear that? Hey, success! Yes, exactly. All right.
That's the loudest noise ever.
So let's see if that makes sense though. Why did the acetone have a higher vapor pressure? They were at the same temperature. Why did this have a higher vapor pressure?
Weaker bonds.
That's it. This, with the hydrogen bonding, pretty much crushed this one. The hydrogen bonding is what explains that this has the stronger overall IMFs, the stronger, I'll say, total intermolecular force. That made its vapor pressure lower. Does that make sense?
No.
Ask a question.
It makes perfect sense. The stronger bonds means it's less likely to evaporate.
Like if they're stuck together more, their tendency to go into the gas state is less because, okay. All right, now, a lot of slides, lot of slides, lot of slides. Now what's interesting about this is how it relates to, that's graphics, how it relates to, got cut off. Sorry, how it relates to boiling point. It turns out that the boiling point of a liquid occurs when the vapor pressure equals the outside pressure. Let me open up a graphic of this because for some reason it got cut off on my fan. But this is cool because I can show you something that you may have heard of but never seen before. And I like doing stuff like that because it's cool. Oops. This also explains why there's different cooking directions when you're in the mountains. If you're going to make rice or noodles or something. I gotta zoom in. I was hoping you were Mr. Clem. Go find Mr. Clem. Everybody's looking for him.
Really? Why?
I don't know. They just keep going, Mr. Clem here. I'm like, no.
Oh, your students or random
No,
students coming
just
in?
random people.
Oh, I was like, if it's your students, I'm not gonna find
No, that's fine.
it. Okay, I'll find it.
Good.
Just
All right.
the cases.
Sorry, guys. Let me get this in a better position here. I don't know why I'm having.
That's cool. No.
Yeah, make sure you leave the cake. This reminds me of the Godfather. You ever see the movie The Godfather?
Yeah.
When they kill the guy in the car,
Are you
like,
looking for
Are you
Clem?
looking for Mr. Clem?
leave the gun, take the cannoli.
We have another. You know where Mr.
Take the
Clem is,
pill.
right?
Yeah, go that way.
All right, I'm gonna find him. Everybody shut up. I'll be everybody's savior, the hero again. It's okay.
Hey guys,
Are
it
you
worked.
canceling this
We
trip?
got Rebecca to leave by saying we were looking for something.
You guys did it.
All right, take a look at this graphic. This shows vapor pressure versus temperature, right? So far it makes sense that as the temperature goes up, so does the vapor pressure. Actually, it's exponential. Now watch this though. Every one of these molecules doesn't follow the same curve. What can we infer? Well, diethyl ether gets to a very high vapor pressure at a very low temperature. But ethylene glycol at 100 degrees is barely shifting the nozzle here. It's barely going up at all. What do you infer from this in terms of intermolecular force? Yeah.
Ethylene glycol has more intermolecular force, like energy. Kind of.
Stronger IMF,
Yeah.
and this probably has the weakest. Now here's what's interesting about this. If I showed you their structures, you'd be able to rationalize that the way we've been talking. But for now, just the data tells us this. Now you'll notice that what we call the boiling point of water at 100 degrees hits this line. But I also want you to notice
That's atmosphere.
that's standard atmospheric pressure, isn't it? So when we say normal boiling point, we have to be specific because we're defining a particular vapor pressure at which it happens. Here's why. In general, boiling point occurs when the vapor pressure of a liquid is equal to the external pressure. So it's really, let me write it this way. It's the temperature at which this is true. But what does it mean to boil? This is the thing that most students don't understand. This is a big misconception. What does your eyeball associate with boiling liquids? What do you see and say it's boiling?
Bubbles.
The bubbles. What's in the bubbles?
Gas.
What gas?
Carbon dioxide.
I just.
Oxygen.
That's the
Water-
misconception.
Water vapor. It's the gas of whatever you're boiling.
Yes, it's the vapor of the liquid. So if this is water, then in here it's water vapor. So this is H2O gas versus H2O liquid. It's the bubbles of the liquid. But why do they open up when it's boiling? Look at what's going on here. The external pressure over the liquid is based on, oftentimes in our experience, the atmosphere, right? But that compression stops the bubbles from opening until the vapor can push just as hard as the outside. That's why usually to boil a liquid, you raise its temperature until the pressure it exerts equals the outside pressure, and then the bubbles form. And we say, oh, it's hot, it's boiling, right? For water, that happens at 100 degrees, or 99, or 98, or 97, or you can boil water much colder, as long as you do what?
Lower the pressure.
Make the pressure around it less. I'll prove it right now. By the way, the normal boiling point, the only difference in the definition is that the temperature at which the vapor pressure equals standard atmospheric pressure. In other words, 1 atmosphere. So, what I have here is water. And inside I got some little chips. They're called boiling chips so it doesn't bubble violently. Hold that. How's it feel? Hot or cold? How does it feel? All right, watch now, people.
Wait, what's in there?
Water and just some boiling chips. Cool. All right, I'm going to take this vacuum pump and I'm going to attach it here, and I'm going to try to make this boil by just pumping the air out. There is a finite chance this could implode.
What? Nice.
So like what percentage of a chance? Just, you know.
Implode.
1.
Oh.
One chance.
Look, it's boiling.
Oh.
Drop it.
I don't want to touch it now because if it's boiling, it must be hot, right?
No.
But it's boiling.
Same temperature, different pressure.
Well, you're touching the glass
In
part.
fact, I got the pressure down as low as I can on this thing. Once I restore the pressure,
Whoa. It's like
it stops boiling.
champagne bottle.
Opa. So what does this mean? This means that by me, instead of raising the water vapor's pressure up to outside with heat, I pulled the outside pressure down to water's vapor pressure at room temperature. So I boiled the water at somewhere around 20 degrees Celsius. It was still boiling, it's just not hot. We're just so used to the only boiling liquid we experience being water that it always is hot, right? But what if you're on like Mount Kilimanjaro and you want to make noodles? First of all, you should have something better to do than make noodles on Mount Kilimanjaro. But if you're boiling water, yeah, it's going to be warm, but when the when the outside pressure is lower than normal, your boiling water is going to be colder than normal. And so that's why if you look at noodles or rice, it says high altitude boiling instructions. It makes you cook it longer because it knows the water temperature is lower. So I just thought that was an interesting thing to think about regarding intermolecular forces and the effect of pressure on boiling. Now, let's look at a few more properties, and then we can get on to the lab piece.
So the water didn't get hotter.
Next. That's right.
Yeah.
Thank you. The next property you need to know is called surface tension.
I
Yeah.
remember this.
Wait, so why doesn't it get as hot?
Because boiling is not heat. Boiling is heat to us because the only liquid we regularly experience boiling is water. And since its intermolecular forces are so strong, in order to make it match the outside pressure to see the bubbles form, we have to heat it quite a bit. And so water does get hot to boil in an open container. What I did is I sealed the container and pumped the air out from around it. So its natural vapor pressure was high enough to make the bubbles. So it didn't have to get hotter.
So what caused the bubble?
The fact that the pressure around it was less. So think of it like this. The preventing of the bubbles from opening is the fact that the outside pressure is compressing the liquid and smushing the bubbles. What I'm doing is I'm decreasing this so much that the natural vapor pressure of water at room temperature is enough to open up the bubbles. It's no more compression because I took the air from around it away. Christine, you had a question?
Yeah, so maybe I'm like mixing up like concepts in my head, but how do you like, if something was like really like had like a large mass and it had like maybe like 2 or 1 like force things, and then there's like another molecule that was like smaller and had like all 3, like what would the, how do you know if, sorry, I can't.
No, I understand exactly what you're asking. This is kind of a feel thing right now, and so usually the questions are going to be phrased in ways that they're similar in size, so it's comparable.
Okay.
If it's not, then they'll give you something that looks anomalous, and then you'll have to make the judgment and say, oh wait, this tells me it's got a higher boiling point, so I know it must have the stronger IMFs, and therefore the dispersion must just outweigh the hydrogen bonding in this one. So it's gonna be done in a way that's fair, because you're right.
Okay.
If it's completely all muddled, it's really, how am I supposed to know how many of these is worth how many of them is, right?
Yeah.
That's a good question. Okay, now, surface tension, this one has a very formal definition. Here's what I want you to know. It's how hard it is to break through the surface of a liquid. Why is it hard at all? Because when you look at the surface of a liquid, what do you see? You see molecules that are part of the liquid, but they don't have similar molecules around them on every side. In other words, when I'm in the center of a liquid, I'm surrounded by my brothers and sisters here, and we're all pulling on each other the same with our IMFs. But when I'm at the surface, there's no one up here. And so what happens is at the surface, they kind of pull sideways and they're pulled inward. And that's why we see that familiar effect of like when you beat up water, like on a raincoat or on a waxed car, the water kind of collects in a ball instead of spreading out. That's partly due to surface tension.
puddles.
Well, puddles are a little different, but when it bowls up is what I'm talking about, not when it just... But what's going to tend to make a strong surface tension? Strong intermolecular forces, right? Same idea. This is why I can take something like a paper clip, which has a much higher density than water, and let it sit on top. And if I do this really carefully, we're going to give you a chance to earn some extra credit.
Oh, I'm doing this.
Okay. I'm going to float this on top. And so you can all see what it looks like. I'm going to pass it around. If the paper clip stays on top the whole way through, everybody looking at it, passing it around, then you get 5 extra credit.
Wait, what happened to our extra credit?
I don't know what, like, it happened.
But I think you put it in. He did.
All right.
Yeah.
Now, you got to be really careful when you pass this.
Oh, no.
Take a look at it,
Doesn't count if you do it.
Yeah.
and then pass it on. So what I'm doing is, you just have to pass it around the room without it falling in.
Without the paper clip on?
Yeah.
Is that fast for everybody?
I don't know.
I think the faster we go fast. Yeah, go fast.
And hope for the best.
Maybe
Hey,
Shake it, we'll fail. No, don't lose it. I raised that from a baby. Why are you breaking my balloon?
Here, let me read. Here, Victor. Victor, come here.
The ball.
I want to explain, Son didn't understand
This
the lesson.
styrofoam ball was wrapped in a little bit.
So we have
It worked, yeah. It's the metal that makes the electrons easier to move around.
I just give it to the other guy.
Did you fail yet?
This is neutral, right?
She said, yes, I see it. Okay.
Just set it on the table.
Pulling.
Not quite.
You get
I
it?
wanna, yeah,
Why do you
that's
think
better.
This is so fun to watch. Make sure you look at it for a second so you can see what looks like the water bending like it has
What?
to
Why
go
should
in.
I just?
Yo, wait, let me just touch it. Alright. I don't want to mess it up.
Where it's
Just
like-
everyone just touch it.
Oh, you guys are shaking it a lot.
So he's been
Yo,
just
everyone
knocked
just
off.
touch it. Just don't move. Just give me. Just tap it. No, give it.
You gave it
Just
to
look at
him.
it. You don't
It's
even
okay,
need
let's
to-
move it on.
Just put it down and everyone just touch it. Come on, just put it down. Put it down.
Yeah, let us still.
Everyone just touch it.
You just-
Everyone touch it. Just touch it, but don't move it. It's gonna count.
Yeah, what he said.
No, just there we go. You good?
Go ahead.
Hurry up!
Hurry up, bro.
Calm down.
Hurry up, touch it.
Hurry!
Just come and look, it's fine, you got it this far.
Yay.
Just make sure you look at it at least.
Plus 5. Let's get it.
How do you think I looked at it? Like 6 months.
You guys did better than I expected. No, don't break it. It wasn't that hard. But if you look at it carefully, it looks like there's a skin, right?
Yeah.
Now, here's the thing. Oh, I failed.
Yeah, so
I failed. I lose points. Now, here's the thing.
What's your grade in the class?
0. So,
His grade goes up.
here's what I want you to know. Surface tension follows the following pattern. Again, if we look at 2 effects, there's the IMF effect, and there's the temperature effect. When it comes to surface tension, listen up now. If the intermolecular force is higher, how should that affect the ability of the molecules to stick sideways to each other? Also higher. Notice this goes the opposite way that vapor pressure did. If the temperature is higher, what should the surface temperature be? lower, because if the molecules are moving more, they can't hold together as well. You see, once you understand the basic idea, and I tell you a property, you should be able to then say, oh, this is how it affects the property, right?
Temperature and surface tension are
Inversely.
proportional.
Right, exactly. And that's why when you wash your clothes in hot water, it helps loosen the dirt and get it into the wash better. Now, the next property I want to look at is called viscosity. This one you guys know. Viscosity is just resistance to flow. Check it out. So, here, yeah.
Is IMF and temperature always going to be inversely related?
They're going to have opposite effects, yes. That's right, yes. All right, watch this. You guys have seen this before, I'm pretty sure. This is corn syrup. This is the junk that almost all your food is sweetened with nowadays. Watch what happens when I pour it
Is it
in.
natural or artificial?
Yes. That is very viscous.
It looks like honey. Like,
It is like honey.
can we try it?
No.
Can we taste it? I want to
Honey
taste
is
it.
very delicious.
Wait.
Okay, okay.
Isn't honey
This
very
one,
delicious?
this is just water. Look at the
Can we
difference.
have a taste test?
You see the difference in how they pour.
I think it's,
Water looks a lot looser when I shake it. It pours very easily, and it doesn't resist its motion very much.
It's not as thick.
It's not as
Not as
viscous.
viscous. Come on, use the new
This one is a lot more viscous, and you can see it doesn't shake as well, and it pours a lot oozier.
Are you looking for clam lips?
So, let's discuss what's going on here. When it comes to viscosity, same idea. When there's stronger intermolecular attractions, the molecules are stuck to each other more firmly, and they don't slide around as well. But like anyone who's ever cooked with honey knows, if you heat up honey, doesn't it become waterier? Like it gets thinner? For the same reason.
increase temperature, decrease in viscosity.
Yes. Now here's another way to measure this. It's actually interesting. Consider this. Here are two liquids. Each of them are sealed, and there's a bead in each one. Which one do you think is more viscous? Ready?
Follow
The one on the right goes to that
The one that takes longer to.
No, you're
All right, we can do this. All right, watch. Which one is more viscous? Right. This one, right?
Yeah.
Okay. Now,
The left one was faster.
not necessarily, but
Viscosity of what?
Yeah, that's why
Sensitive. Okay. Now, capillary action is another connected property. Watch this one. For this, I have a nice little demonstration from far away. These are 3 different diameter tubes, right? Now, it turns out that depending on the intermolecular force interactions, certain materials wet each other or stick well, other ones don't. When they stick well, it's called adhesion, when it sticks one thing to another. So we all know that water kind of adheres to glass. Water sticks to glass. When we look at how strongly they attract to themselves, we call it cohesion. Now watch what happens when I take these 3 different diameter tubes and dip it into this colorful green water. It's going to dip it in, I'm going to raise it back out. And what you'll see, I don't know how far away you can see it, but you see in the thinnest tube it goes up really high.
Yeah.
In the second diameter tube it goes up somewhat, but in the fattest tube it doesn't climb very well. This has to do with adhesion versus cohesion. And it also has to do with the thickness. The thinner the capillary tube, the higher the liquid can climb. This is how root systems work. What? The thickness does, but what if I was using liquids that did not stick as well to the glass? Would they climb? You get what I'm saying? So the intermolecular forces and the attraction between it and the surface matters. So let me show you what I mean by that. So, when you look at something like mercury, mercury is a nonpolar liquid. Glass is a rather polar surface. Notice that the meniscus is upside down because the mercury prefers itself to the glass. And so it has, in this case, stronger cohesion to itself than adhesion to the glass. But every time we did this stuff about meniscus with water, look at the difference. Every time we read an instrument where water goes into glass, it makes us smile. Because here, the adhesion of water to the glass is actually stronger than its own cohesion to itself. And so it actually climbs up at the edges. The thickness of the tube matters because obviously, think about it this way. If the tube is thinner, more of the liquid has access to the glass, and less of the liquid is in the middle, not touching the glass. Yeah.
So does the glass have a charge?
Not like a net charge, but it has polar sites along its structure.
So it has like an ion.
It has the ability to interact more strongly with polar materials than with non-polar materials because of its surface. Yeah.
If the glass or tube was more like lower or thinner, it would still make that shape.
Even more pronounced. It would look even worse.
So what's a liquid that would make it kind of?
Like mercury, a non-polar liquid typically. Yeah. Not exactly. Alloys is a whole other thing we talk about later in this unit. We'll get to that. Yeah.
What is like the chemical structure of glass?
Well, it's basically a silica, so it's like just taking sand and melting it, and then you get like this kind of random structure. So that's why it's kind of considered by some as a very viscous liquid, or as an amorphous solid, because it does kind of flow over time.
So like what elements? Like we don't like just all.
Oh, silicon dioxide mostly, and then other things that are added in for properties. So it depends on the glass. Yeah. Just bring it when you get it. That's fine. All right, we're going to do this lab now. So you guys are going to watch a couple quick demonstrations about what we've been talking about, and then I'll have you write it out. But it's actually really simple. Need more?
Yeah.
No, I got you.
We have an extra.
You need one more? Okay. So, at the bottom are the three liquids that we don't know who's who. Okay, so watch this now. Each of these I gave you the Lewis structures so that we can look at what kind of polarity is in each one. So if you look at hexane, isn't that all nonpolar because it's all hydrocarbon?
So
Just dispersion. Ethyl acetate is mostly hydrocarbon, but it has that polar section with the oxygens in it. So for ethyl acetate, we have dispersion, but also dip-dip. And then glycerin, you see all those OH groups? This can not only hydrogen bond, it can hydrogen bond in 3 spots. So this has hydrogen bonding, dispersion, and dip-dip. And so if you flip on the back, you'll see that we're going to do a bunch of quick little tests on properties and try to figure out in unlabeled containers who's who. So the first test is the viscosity test. Here it goes. Here's X, Y, and Z. Let's just rank them. What do you want to call the most? Oh, I have it there. Highest is 1, lowest is 3. So here's tube X. Okay, pretty slow. And then we can retest if we need to. Here's tube Y.
3 at once.
Here's tube Y.
Oh my god.
So that's definitely the most viscous, right? Oh, here's Z. Here's Z.
It's gonna be fat.
yeah, okay. So is that faster than X?
2, 1.
You want to compare with X?
Oh.
Oh, they're close.
Like the same. Wait, no.
So X is right.
I think X is a little more viscous. So put X, rank X number 2 on viscosity. Y was number 1. And substance Z was 3rd. All right. For evaporation, I'm just going to have to count on, I'm skipping the surface tension for just a minute. I might need help.
It's not sterile.
I know I need help.
I was bleeding out my
It's a
nose
long
for like the
story.
past 20 minutes. I've been at a nose since I was like 8.
All right, verification. Are you ready? We're going to the evaporation rank. So what I'm going to do is I'm going to take a Q-tip right in front of this gentleman. I'm going to put a streak line. He's going to see how long it takes to evaporate. Are you ready, gentlemen?
Don't mess up tomorrow.
Don't mess up tomorrow.
This is X.
Don't mess up tomorrow. Count.
Go.
1, 2, 3, 4,
That is
5,
horrible counting.
6, 7, 8,
X is about 10 seconds. Here's why. Ready? Here's why.
1, 2.
Well, that one's gonna take the longest.
Okay, good. You can stop counting that one. That ain't going no place.
Yeah.
Y is definitely not going no place. No. And here's Z.
Dead.
Believe me, it's not cologne. Ready to count Z? Go.
1, 2, 3, 4, 5, 6, 7.
That's already gone. This is, I put too much here. Look.
Oh, that's all.
Oh, okay.
So wait, the shortest
So
time
it's
was
the same.
The highest vapor pressure was Z because it evaporated right away.
So it's the opposite.
Wait.
Yeah, we want the highest, right? So the highest vapor pressure, or
It just says evaporation.
so think of it as vapor pressure, like how fast it evaporates. So we said, which one? Z was the fastest.
So fastest is highest or fastest is lowest?
Fastest is highest.
Okay.
Number one. We said Y was the least evaporative, like it sticks around the longest. And X was in the middle, okay?
So
What about surface?
Y and Z.
All right, we'll get to that. Miscibility, I can do this one really quick. That has to do with how well they mix. Check this out.
Like, guys, would you like Toy Story?
Are you gonna watch the new one that comes out?
Do not say that.
When do you need help?
You're
Oh, no,
about
I'm
to say
good.
it looks like Al.
I'll get you one.
Oh.
All right, wait. Listen up. Next one, quick. Sorry, I know I'm going fast. X, Y, and Z were all mixed with water. Here are the results. Here's X in water.
If I drank that, would I get?
Can you guys see what's going on here? The water's been colored green, just so you can see it. But you see another interesting thing, look at the shakiness. You see this is less viscous than the water? But right now, does the water and X mix?
No.
So for that, where it says miscibility,
Their density is different.
this is,
X.
for X,
Non-polar.
does not mix in water.
So NP.
So we're saying that X is definitely non-polar based on that. Because remember, things of similar polarity mix well. Y completely mixes, so we know that Y is polar because it mixes with water.
Y is polar.
If I drank that, would I get?
And then Z is mostly non-polar again because they don't mix well. Okay? Then we did a similar mixing experiment but in a non-polar solvent called pentate. So here is X, and you can see there's no line of separation. So since this is a non-polar solvent, that again shows that X must also be somewhat non-polar. Here is Y, and you can see in Y they don't mix well at all. So in the non-polar solvent, Y does not mix. That makes it polar. And then in Z, again, in the non-polar solvent, it mixes fully. So it's totally miscible. So in this case, again, we show that Z is mostly non-polar. Okay so far? Now,
Oh, wait, hold on.
yeah,
Z is non-polar.
Yes.
yes, relative to the mixing test, it is. Now this is the tricky one to do surface tension. I'm going to do a really stupid experiment.
Yay.
I'm going to see how many drops I can stack on a penny before it
This is
collapses.
a great call, bro.
Here's
Oh,
X.
no.
All right, don't mess me up. I got to count. And then I got one more quick demo that I think you'll like.
So this one's a measure of the surface
4,
tension.
5, 6,
No.
7, 8,
Yeah.
9, 10, 11, 12, 13, 14, 15, 16. It collapsed already. Didn't it? I'd say 15 of X sat on a penny before the bulb collapsed.
Are we supposed to rate that?
In
We have to wait
Surface
until-
tension, right?
surface tension,
You don't
just
even
how many
rate it?
drops.
Oh, I thought we.
And then I'll tell you, we'll rank them after. The next one is, oops, Y. Sorry, I'm just trying to beat the clock here. Thought I could make it. I might make it. All right, here's Y. So the first one was 15. Oh God, this, I'm not even gonna be able to do this in particular.
Just
One.
infinite drops.
2, 3, 4, 5, 6, 7, 8. Can't even get the stuff up in here. 9, 10, 11, 12, 13. I haven't even covered the penny yet. 14, 16,
We get it.
17,
We understand.
19, 20, 21, 22, 23, 24, 25. 5, it's making a nice ball. You see it?
It's a perfect shape.
Is this X or Z?
6, 27, Y.
This is Y.
28, 29, 30. 30.
So that's gonna be number one.
So that's definitely going to be the most surface tension. And then Z, Z goes, well, oh God. As soon as I poured it out, it fell over.
Z's gonna be
0.
0.
1, 2, okay, 5.
So what?
Yeah,
that's
1.
3. Z is
All right.
3.
So, here's what I'm going to do. I'm going to let this one ride and let you guys try to finish this up tonight instead of the other paper. I'll give you the other paper tomorrow, I think.
Can you give us the formula?
One last quick thing. Watch this demo. I've been saving this one for last because it's cool. Like dissolves like. Meaning, because of intermolecular attractions, things of similar polarity mix well. Watch this. This is ethanol.
Highly
Now, watch carefully. This is really cool, I think. Next, where did I put my glue? Oh, I'm going to take the tiniest bit of iodine and drop it in there. Okay? Iodine is nonpolar. I need a really tiny bit. That's way too much.
What the hell?
I'm trying to break it into a smaller piece.
I hit this as hard as I can.
No. All right, watch. Tiny bit. Did I get it in there? Oh, you see the yellow?
Yeah.
Oops.
Give us the least dollar.
Now watch this.
Yeah.
Hexane. Hexane is also nonpolar. I'm going to pour the hexane in.
What is hex?
We'll draw the structure in a moment. Now, do you see how they're still kind of mixed?
Yeah.
Now watch the cool part.
Are they gonna explode?
Not exactly. Let me shake it up and make sure it's fully mixed. So far, if you look, what you see is the iodine dissolved in the ethanol and the hexane all mixed. But there's something weird going on here. Let me show you what I mean. Iodine is definitely nonpolar. Hexane is just this. Also very nonpolar. But ethanol is this. Alright. Am I losing you? Is that what you're saying?
What's add heat? In a sense. That's what you lost it. Add heat.
So right now, all three of these are mixed and they're completely mixing together. Watch what happens when I put water in. This is the
Oh
interesting.
no.
It's gonna be like soap.
It's gonna blow up.
Alright, let me pour it in here.
I would love to see an explosion right now, I'm just saying.
Alright.
Go
On a
back
scale
my
of
day.
1 to 10, how
Oh.
There's a little bit of an explosion.
No. That is
Shake it up.
the least explosion possible.
Now I'm going to stir it a lot and see if I can get it all to stay mixed.
You get soap.
Watch what happens now though.
Pink.
Look at the color.
Oh, it's like becoming red.
Not as only is it becoming red, it's separating into layers.
Oh.
See that? So what happened here was this, and this is a really good point about solubility. Solubility is not a yes or no question. It's a question of degree. Who do I stick to better? When these were the only ones in play, they all played pretty well. This has a pretty big hydrocarbon piece that can interact pretty well with this and with this, all nonpolar. But doesn't this have the ability to do something polar? So once I put water in the mix, the effect of the water was to grab this piece out and separate it and pull some of the iodine along. So the iodine mostly stays in the hexane part, but the alcohol gets pulled into the water part, and that's why we get a separation afterwards. So I just thought that's a cool way to show that solubility is not just yes or no. It's a question of who do I have to play with and who do I want to play with more. Yeah,
Oh, did you add the colors or to like show us?
yes.
Okay.
I did all that on purpose. The iodine is the color,
Right.
but in one solvent it has a slightly different color than another.
Okay.